with this, so again, that bottom example document we'll come back to and deal with quite a bit. And I'm on the wrong slide here. Yeah, chapter 13, equilibrium. We've talked about equilibrium already this year. We have twice. We started talking about equilibrium in chapter 17 when we did thermodynamics. Then in the kinetics chapter, there was a little bit of talk about equilibrium and how we use K in the mechanism to try to figure out what the rate law for a reaction is. Now we're going to have 4 consecutive chapters that deal with equilibrium. 4 of them. So we'll finish the first semester in these 9 days. And by the way, I have checked the weather forecast. It looks really good for us to go these 9 days and not have a snow day. I don't care about snow days after this, but we need to get this in before the first semester ends. So it'll be good to get this knocked out. So chapter 13 is a general equilibrium chapter, and we'll use what we learned in 13 a lot when we go on to 14. 14 is about the equilibrium of weak acids and bases. Because as we talked about back in chapter 4, a strong acid or a base completely dissociates. But a weak acid dissociates a small amount and then stops. Well, it comes to equilibrium. So we'll have to go into what the equilibrium is like for a weak acid or a weak base. Then chapter 15, that's what we'll start the second semester with. Traditionally, chapter 15 is one of the tougher ones. People do remember chapter 15, the buffer chapter. It's more complex and detailed than 14. 14 is not terribly difficult. People tend to do pretty well. I'm not saying it's easy, but it's not one of the hardest. You hear me? It's not an easy chapter. 13 and 14 are not easy, but they're not one of the hardest, or 2 of the hardest. So yeah, but 15 is known as one of the tougher ones. We're going to just kick second semester off with that. And then chapter 16 is about the equilibrium of things that don't dissolve very well. When you put something into water and a little tiny bit of it dissolves, but then it just doesn't dissolve anymore, it came to equilibrium. So it's the solubility equilibrium that we'll take on in 16. So chapters 13 through 16, 4 chapters, are all equilibrium. And then by the time we're done with 16, you'll be very glad to be done with equilibrium. There'll be a lot of repetition over these. 15 to 16, it will take about a month. It'll be early March. We'll be getting done with equilibrium. So yeah, it's long. Okay. Now, as a reminder, this is not new to anybody. We have this relationship relating the delta G of a reaction to the K value. This, notice, is the delta G naught, the standard delta G. When this delta G, the non-standard one, that's constantly changing as a reaction happens. Reaction starts and the delta G is not 0, and it changes constantly as products are made, and then as soon as this delta G hits 0, boom, that's it, the reaction's over. There may still be reactants present, but the reaction has reached a point of comfort. I do want you to know, mentioning this top line, even though a reaction comes to equilibrium does not mean that the reaction is not doing anything. It still could be happening. The forward direction can still be happening in making products, and the reverse reaction can still be happening in making the reactants. The thing is, at equilibrium, they're the same rate. They're happening at the same rate. So you, from a macroscopic view, cannot see any change. You can't see anything going on there when the reaction gets to equilibrium. Okay, so we have this. Now, one quick thing about this relationship, this makes it look like the delta G and the K are related to each other, which they are. But I will also let you know that K is dependent on temperature. If we change the temperature, this K value will change as well. This equation doesn't show it very well, but we have another equation we're going to see in a moment there that is going to be very clearly showing how K changes as the temperature changes. K is temperature dependent. So we call it the equilibrium constant, but it's only good at a certain temperature. You change the temperature, the K is going to get thrown off, and the reaction will shift. So another, just a review slide about this. This slide actually has a name for it. I didn't use the name before, and I won't use the name after this. But this is based on a scientific law, the law of mass action, that says that when a reaction gets to equilibrium, then the K value is the ratio of the products over the reactants. Now, I'm showing you the products over reactants in terms of molarity. When I use brackets like that, it means molarity. Like when I put the brackets around HCl or whatever, that means concentration of HCl. When we learned first about equilibrium constant, I was giving it to you in terms of pressure, the pressure of the products over the pressure of the reactants. You can either determine the equilibrium constant with concentrations, like is shown here, or pressures. And I'll deal with the difference between those two later this hour. We'll talk about how those are different. Don't be intimidated by the fact that there's an EQ down there with the K subscript EQ. It just means equilibrium constant. There's no other hidden difficult meaning to it. So anytime you see KEQ, just find the product over reactant ratio. Okay, now this slide, I'm going to show you something about the relationship between K and temperature today, and then I'm just going to let that simmer with you. In a couple of days, we're going to do this very thing again, and hopefully the second time you see it, it will make sense. I don't expect it to make any sense today, so don't have high expectations for what you're about to see at the bottom of this column, or this slide. It tells us in bold here that there's only one thing that will affect the value of K for a reaction, and that is the temperature. Nothing else changes the K value except for changing the temperature. And this relationship is from chapter 17. And when we were doing chapter 17, I ran out of time. I didn't have time to show you this, so I actually cut several of the questions out of the practice test. I said, hey, don't do this list of questions in chapter 17 because we did not get to this. So here it is now. This actually is combining this, wrong, delta H minus T delta S both of these are expressions for delta G. And when we set them equal to each other and then just solve it for ln of K, this is what we get. So yeah, you can see how this would have come out of the thermodynamics chapter. Now what I want you to know is that delta H and delta S, those are not dependent on temperature. So these two terms are constant. R is a constant. So here's what we have. We have the temperature changing, causing the K value to change, where that's a constant and that's a constant. And you've seen this at other times in this class. We have a variable equals a constant times another variable plus a constant. It really is the equation for a line. Now this line is totally inconvenient. It's a mess because look at what our X term is, the inverse of temperature. Look at what our Y term is, the natural log of K. This is as close as we can get to the relationship between K and temperature. And that relationship looks like this. It's a graph. And on the x-axis, we put 1 over temp. On the y-axis, we put ln of K. And now we let the rest of these constant values dictate how the graph looks. If it's an exothermic reaction, take a look at, I'm going to erase this part. I'll erase that too. Take a look at this slope. This is the M term, the slope. We got negative delta H over R. So if it's an exothermic reaction, the delta H is negative. A negative of that negative delta H makes the slope positive. So you're going to have a positive slope if it's an exothermic reaction. If it's an endothermic reaction, it'll have a negative slope because you'll have a positive delta H with a negative sign out in front of it. Makes it negative. So if it's an exothermic reaction, it's going to have a positive slope. And what this is telling us is this. This is so complicated and you have to wrap your brain around. Again, don't feel like you're going to be behind if you don't catch it this time. Nobody will, I don't think. The temperature is the inverse, the x-axis I should say, is the inverse of temperature. It's the inverse of it. So as temperature gets big, we're down here, close to the origin. When temperature is small, the inverse is very big, because it's the inverse. Now, the y-axis is the natural log of k. As the natural log of k goes up, that means the k is going up as well. So if k goes up, its natural log goes up. K goes down, its natural log goes down. So that means this. If you have an exothermic reaction and you heat it up, heating it up means you're going this direction on the graph. What happens is heating up an exothermic reaction causes the K value to go down. That's what happens. And if it's an endothermic reaction, if I did this in a different color, here's an endothermic reaction. If you increase the temperature of an endothermic reaction, the K value goes up. So we will deal with this in a couple of days. When we talk about Le Chatelier's principle, you might remember that term from Chem 1. We'll get to this, and there is a simpler way to think about how the K changes when it's an exothermic and endothermic. I do need to show you this so you have the background, but then there's a very simple way to analyze exothermic and endothermic reactions and see how the K value changes. But just know for right now, the K is dependent on temperature. The K value will change if the temperature changes. Okay, so this next slide, I'm going to take you to one of the examples in that handout document. So go to number 16. I'm going to give you a second. Open up that document into something that you can write on. I have it in Apple Notes. Go to number 16. Every year, when I look at this document, I kind of shake my head and think, I really should make this a Word document. This was from an old test bank. Old. When I say old, I mean old test bank. Probably from the 70s or 80s. This is typewriter font, not because it's a fancy font in Word. It was from a typewriter. So I look at this and think, man, it's so old looking. Even the way the question is framed is old. I don't know, but there's something that warms my heart about it. So I keep it. I don't ever want to change it. Look at the way they even ask the question. It says, given the values for the standard free energies of formation tabulated below. Tabulated means that they made a table out of it. Well, here's our archaic table right here. We have a simple synthesis reaction. H2 plus CO makes CH3OH, methanol, makes methanol. They give us two of the free energies of formation. See, it says delta GF with a degree sign. They didn't give us the free energy of formation of H2. You remember why? Because it's zero. Right, it's an element. Elements have zero free energy of formation and enthalpy of formation. So, but we're just talking about delta G here. So, yeah, we know that the H2 is zero. So we can find the delta G of this reaction. So what is asking us for? For this reaction, if you know the delta G's of formation, calculate the equilibrium constant at 298 Kelvin for that reaction. So we really haven't done anything yet with equilibrium, but I would expect you to be able to do this because this is really from chapter 17. We're going to use okay, why is my marker must have shut off? I'm having trouble. Okay. So this is what we're going to wind up using. If you can determine the delta G, which you can find the K. I'm going to give you a couple of minutes. Do that. Determine the K value, the equilibrium constant for this reaction. So let's see, for the delta G, products minus reactants, we're going to get negative 24.6, if I remember right, kilojoules per mole, equals negative R. R is 8.31. That's in joules, though. Since we are given kilojoules for our delta G, we'll use 0.00831 kilojoules per mole Kelvin. I'm going to run out of room bad. Temperature is 298 Kelvin. And then that's times ln of K. Oh boy. Yeah, now back when we were doing chapter 17, I was trying to protect my Algebra 2 students. I was telling you, hey, I'm not going to give you anything where you have to find the K if it's in an ln in the formula. But then in chapter 12, I think we did that. We started to take the inverse function. So just a review of doing that. Let's go through. Do we have an answer? What's your multiple choice answer? A is correct. It's A. Yep. Because, let's see, if I get the ln of K term by itself, just divide out that term and that. Don't forget the negative. And we're going to have, the negatives do cancel out. This negative and that negative are going to cancel out. It'll give us ln of K equals 9.93. I just kept 3 sig figs, so everything's got 3. So now, if we need just the K value, we have to get rid of that ln term. So we have to use the inverse function of the ln, which is e to the power. So we just raise both sides of the power on e, and then the ln goes away, and we have just K equals, and it'll be e to the 9.93 power, which winds up being around 20,600, which is A. Yes, sir. Oh, it's products minus reactants. You were given the delta G of formation of CH3OH, and then the CO, and we know that H2 is 0. So it's just products minus reactants. Delta G of the reaction. That's how I got the negative 24.6. Anything else? Okay, so now going back to this. The next thing, this is going to look like Hess's law. So we're going to use another thing from the thermodynamics unit. Take a look at the chemical equations that are given here and look at what the title says. The title says, if the equation gets manipulated, what happens to the K value? We're not going to look at numerical value. We're just going to look at what the K expression should look like. If we have just two reactants and two products, A plus B in the reactants, C and D in the products, the K expression would be concentration of the products on top over the concentration of the reactants. I'm referring to this as K1. We're going to compare this and this to K1 because you can see that we're just taking this first equation and manipulating it. In the second equation, we're multiplying that first equation through by 2. What does that make the K expression if we take the first and multiply it through by 2? Well, let's just do the raw K expression. It would be the products, which is C squared times D squared. Remember, the coefficients become exponents, over A squared and B squared. Now, from our algebra knowledge, we're aware that when you have all these squared terms, that's the same thing as C times D over A times B, all raised to the second power. Isn't it? Aren't these two things written in blue the same? There. That's true. Okay, well, how does K2 relate to K1? What do you see there? This inside the parentheses looks familiar. That is what K1 was. So this thing is equal to K1 squared. So this is what we see. I know that this looks like some of the technique that we used in Hess's law when you had a delta H for a reaction. In Hess's law, if you had to multiply through by a coefficient in all the terms, then you would just multiply the delta H by that. However, when it's an equilibrium constant, you don't multiply the K by 2, you raise K to the second power. It's an exponential change, not an additive change. So be careful with that. Now, what about this one? Knowing that the change that we apply to the equation causes an exponential change, let's take a look at the third example. We now have the original products have become reactants. The original reactants have become products. So the equilibrium expression would be A times B over C times D. How does that relate to K1? Is the inverse. Yeah, it's the inverse of K1. So it's 1 over K1. Or K to the negative 1 power. So since we kind of multiplied this thing through by negative 1, we turned it around, the K gets raised to the negative 1 power. So with this has a Hess's law feel to it, but don't do the same thing with K as you would do with delta H. So be aware that there's a difference with the equilibrium constant. Now, the next 3 slides, it just asked us to do 3 different examples. We're going to do example number 2 on the document, example 3, and then number 4. Whoops. So yeah, I'm not going to come back to this one until we've done numbers 2, 3, and 4. So let's go there. Number 2, what I'm doing here is with number 2, what we just saw about Hess's law does not apply here. It's really the next thing. We have in number 2, 2 given equations, and they have an equilibrium constant for each, and then we have a target equation. So it's pretty easy to see what we had to do with the given equations to get to the target equation. You don't have to manipulate them at all. Just add them together. That equation plus that equation gives us that equation. So let's take a look at the K expressions for these. I'm going to start with the target equation. I have reactants and products. The K expression for the target equation would be D times E over A times B squared. that is the K. It says the equilibrium constant is, that is the equilibrium constant. However, it's not in any of the multiple choices. It gives us the choices all in terms of K1 and K2. So what did we have to do with K1 and K2 to get that equilibrium constant? Well, let's take a look at K1. K1 for the first reaction would be the products, C over the reactants, A times B squared. And K2 is the products of that one, D times E, over the reactant C. What do we have to do with K1 and K2 to get this? Multiply them. So that means when you add two equations together, listen to this, when you add equations together to get a target equation, you don't add their K's, you multiply them. Multiply the K's. So the answer for this one is D. We got the KC here by multiplying K1 times K2. You can see when you multiply these two, the C's will cancel out. We'll be left with D and E on top, there they are, and A and B squared on the bottom, there they are. I don't know if Germain Hess from Hess's Law fame ever did anything with equilibrium. We can see that we can add equations together to get target equations, just like we did at Hess's Law. But this is, I've never seen it called Hess's Law. I'm relating it to Hess's Law with you, but I don't know if that's actually part of his law. Let's go to number 3. Same kind of thing. We're given two given equations, and then we have a target equation. We want to try to arrive at that target equation by manipulating and then adding together these. All right, now take a look. You're good at Hess's Law. What would we have to do with the first equation? Don't worry about the K, but what would we have to do with the first equation in order to achieve the target equation? Harish, what do you do? Okay, we have to turn it around. Something else, though. You don't see it? We have to turn, look at this. In our target equation, we have SO2 with a 1 coefficient. Up here in our given, we have SO2 with a 2 coefficient. See that? So not only do we need the SO2 turned around, got to divide it by 2 as well. So this thing is going to have a negative 1/2 multiplied through it. The negative is to turn the equation around. Then the 1/2 is to cut all the coefficients by 2. That'll give me 1 SO2 on that side. What about NO2? We have NO2 where we want it. It's on the left, but it doesn't have the right coefficient. So we're going to not turn the second equation around, but we do need to divide the coefficients by 2. So this one is just going to be times 1/2. Okay, so I'm not doing anything with the K's yet. We'll just take the equations and we'll say, okay, this first one is going to turn around. It's going to be SO2 plus 1/2 O2, 1/2 is fine. It's an equilibrium sign, makes just SO3. I had to divide all the coefficients by 2. The second one is going to be not turning that one around. It's going to be NO2 yields NO plus 1/2 O2. Now, we will be able to add these two together and get this target equation. The 1/2 O2s on both sides cancel out. That cancels that. Everything else is good and accounted for. Now, what about the K's? These numbers were given like this because they're should be pretty easy to see what they are. Do you know 225 as a perfect square? Yeah, we should know our square roots at least through 15. So yeah, this is 15 squared. And then 64, you know that one too. So when we had to manipulate this equation, it had to be turned around, which makes the 225 go in the denominator. And then we had to take the square root of it. So we're taking 1 over the square root of 225. So the K now is 1 over 15. See that I did two things to the K. I turned it around, the equation around. That means I take the inverse of that. So it's 1 over 225. But then I had to cut it in half, which means I take the square root of the K. Daniel?
So this isn't like the traditional Hess's law where the G and the G values or K values like flip around, like turn into K.
Right, yeah, the K cannot be negative. So you don't ever just slap a negative sign on it. But whatever you do to that becomes the exponent on that K. So it's K to the negative 1/2 power. Rather than putting a negative sign out in front of it like that. Yep. Again, K cannot be negative. It's ratio of products over reactants. You can't have a negative amount of products or reactants. Okay, so the next one, we didn't have to turn that one around. We just took divided the coefficients in half, which means we have to take the square root of 64. So this K value is 8. So yeah, for this reaction, the K would be K1 times K2, which would be 8 over 15. And that is just over 1/2. 8 over 16 would be 1/2, so it's just over. Looks like D is our choice. All right. Now it's your turn. Try number 4. Number 4 is not bad. I think the one we just did was the hardest of these three. See what you can do with number 4. Got an answer? What do you have to do with equation 1? You have to do anything with equation 1? No, just leave that alone. We've got 4 NH3s on the left. That's exactly what we want. What about equation 2? What do we have to do with that one? Multiply by 2. Yep. Because we need the 4 NOs to cancel those NOs, so I need another 2 of those. I have to multiply by 2 because there's no NOs in the overall equation, so they have to cancel out. And then I need 7 O2s, so if I need to put a 2 there to make 7 O2s. Yep. This equation gets multiplied by 2. That means the K2 gets squared. So when I add that plus that one, after I've corrected it, it will be K1 times K2 squared, B. Anybody have any questions about that? Okay. I'm taking you back now, back to this. One more topic to take on, and we should be able to do this easily by the end of the hour. There's 2 different ways that we can describe the equilibrium constant. We can either take the ratios of the concentrations. Remember, when you see the brackets there, that means concentration. Even if this is a gas phase reaction, all 3 of these things are gases. When I give the concentration, I'm not talking about dissolving anything in water. I'm not going to dissolve these gases in water. You can describe the concentration of a gas. Think of what concentration is. Concentration is an amount per volume. So if we're talking about molarity of a gas, it would be moles of the gas per liter of space. So we can actually have a measure of the concentration of a gas. So if I have a Kc, the little subscript C there represents concentration, I would take the ratio of product concentrations over reactant concentrations. That would be Kc. If I needed the Kp, that's the ratio of the pressure of the products over the pressure of the reactants. So there's these two different equilibrium constants. Are they the same? Unfortunately, usually they're not. There are times when a reaction will have the same Kc and Kp value. We'll talk about that in a moment. But what I want to do here at the end of the hour is give you what the relationship is between Kp and Kc. How do you get from one to the other? Now, I will say that what you can see up here, it's subtle, but I want to mention it. If you have a value of K given, and it's not specified whether it's Kc or Kp, an unspecified K means Kc. Just like in the last chapter, I know it was a long time ago, if I said give the rate law for this, you would give the differential rate law. If I wanted the integrated, I would say give the integrated rate law. But if it's done unspecified, it meant differential rate law. Here, if I don't specify which K, I mean Kc. If I'm talking about Kp, I have to use the P. Okay, so I want to give you the relationship in the form of a derivation, a little tiny derivation. Starting with the ideal gas law. We have our good friend, the ideal gas law, PV equals nRT. If I divide out the V, it'll be canceled out from the left. And on the right side, we'll have nRT over V. Now, as we've talked about in here, it doesn't matter what order you do multiplication and division in. I have n times r times t over v, but that's the same thing as n over v times rt. It doesn't matter what order you do the multiplication and division is. You'll always get the same answer. So that is the same as that. Can you buy that? It is. Now, the reason I do that is because n over v is moles over liters. That is molarity. So this thing right here is the molarity. So if I want the molarity by itself, I have to divide out the RT. So that's where I get this line. The molarity of a gas would be its pressure over RT. That's the molarity of a gas. That's going to allow us to change from a Kc that has molarities in it to pressure terms. And so I'm going to go now to the next slide. And in the next slide, I erased it. I'm going to rewrite what the chemical equation is, because we need that. It's this thing. And you've seen this chemical equation a number of times already. N2 plus 3H2 yields 2 NH3s. Oops, I lost my 3 there. It's kind of popping out. Okay, so the Kc, oops, I'm not on the red slide. N2, I'm doing this again, plus 3H2 yields 2 NH3s. So the Kc would be the concentration of the products over the concentration of the reactants. There it is. Remember, the coefficients become exponents. Well, the next thing is to replace what we just did in the last slide. Rather than give the molarity of the products and reactants, we're going to call the molarity P over RT, pressure over RT. And that means this. We're going to take each of these three terms, that, and that, and we're going to replace the concentration with P over RT. It's going to look messy for a moment. It looks like this. Pressure of NH3 over RT squared divided by pressure of N2 over RT, that's to the first, times pressure of H2 over RT to the third. So you see that I kept the exponents the same. Got a second exponent here, first there, and third there. Each of these cases, I took the molarity and replaced it with P over RT. Now we're going to take this thing and clean it up. I have some instructions for what to do to clean it up here. We're going to separate the pressure terms away from the RT terms. The RT are constant terms. So the pressure terms look like this. P of NH3 squared over pressure of N2 times the pressure of H2 cubed. That's just my P terms. Then my RT terms, they're all over the place. We do need to simplify them. They're a mess right now. I have RT squared in the denominator. See how it's in the denominator of the numerator? That means it goes in the denominator. Then I have 4 RT terms. I got 3 there. See that 3? And then another one. 4 RT terms in the denominator of the denominator. So when you have something in the denominator of the denominator, it rises up to the numerator. So I have RT to the 4th over RT to the 2nd. All this is being multiplied together. Because all of it is being multiplied and divided here, I just separated some terms. Why did I separate those terms? What do we have here in that? What I just circled in red, the pressure of NH3 squared over the pressure of N2 and the pressure of H2 cubed, that would be Kp. That's the ratio of the pressures of the products over the reactants. Kp. Now what about this thing? I have RT to the 4th over RT to the 2nd. Where did the 4 and 2 come from? Can we generalize this thing and identify, okay, what do the 4 and the 2 represent? Can you see it? What is it? The moles of gas. Right. The reactants have 4 moles of gas and the products have 2 moles of gas. That's where my 4 and 2 come from. Now, what we're going to have, this is going to equal Kp, that's the part in red, times RT. Now, how do we get that? We took the total of the reactants minus the total of the products. Can I call reactants minus products delta N? Can I use the term delta when I'm taking reactants minus products? We've learned delta is pretty standard. When I say delta, that means final minus initial, or with thermodynamics, products minus reactants. So if I have reactants minus products, which is what I have, there's 4 reactants and 2 products. I got reactants and products. This RT is actually negative delta N product, or delta N. Okay, now what does that equal? That equals Kc. So now we have the relationship between Kp and Kc. This negative delta N, what I'm going to do is I'm going to move that term over to the other side. So I have this form of the equation and it's not a typo. I have Kp multiplied by RT times the term. And then over here I had Kp by itself. It's because I divided out the RT to the delta N power, negative delta N, over to the other side to make the delta N exponent positive. So this is correct. This is the relationship between the Kp of a reaction and the Kc. There is, it is possible for Kp to equal Kc. When would it be? What kind of situation could I have in which the Kp for a reaction was equal to the Kc? Come on. What is it, Daniel?
Like concentration is 0.
What do you say?
Say it again.
When concentration or the pressure of the product.
Nope.
What you asked?
I asked when would you have a situation in which Kp and Kc were equal to each other?
Oh,
Edison?
so when delta N is 0.
Yeah, when the exponent here is 0. I don't know if that's what you were trying to say, Daniel, but that's not what I heard. So if you're, what that means is if your coefficient of your gas reactants and products were the same coefficient, then you'd have a 0 exponent up there, and that whole term would just become 1. And in that case, Kp equals Kc. But if you have a different amount of gas in the left and the right, then Kp and Kc will not equal each other. And this is how we get from one to the other. So if you know one of them, you can find the other using this formula. A couple things about this. The R value that we use in this formula, because Kp is always the ratio of the pressures in atmospheres, you got to use the R value that has atmospheres in it, not the kilopascals R value. So yeah, we have to use 0.0821, the atmosphere's R value. I haven't used that in a while, so that's strange. The other thing, I'll just tell you, I remember this formula with just a dumb memory trick, and literally it's dumb. It's stupid, really. But it helps me. So I'll tell you what I think, and you'll think, well, that guy's dumb. But you can use it or come up with something else on your own. Because I have trouble just brute force remembering. Is the Kp by itself, or is the Kc equal to Kp times R? I don't want to derive it every time. So if I can just remember this, how am I going to remember which one is Kc and which one's Kp? So I think of this, I have named this in my own brain the Prince Charming equation. Yes, it's dumb. This has nothing to do with a fairy tale. Nothing. But what it does help me with is that if I think Prince Charming, I think the P comes first and then the C. Prince Charming. And it works for me. So I know that the P is by itself, and then I got the C and the RT delta N. It helps me to remember what the formula is. We will start tomorrow using this in an example problem or two. So, yeah, I have finished in the same place in all classes today. We'll just pick this up and do more with equilibrium tomorrow. I know today is very tough. As the day goes on, I could just see your body language. It's rough to stay alert and pay attention. Thank you for doing your best today. And get some sleep tonight, for goodness sakes.